Hi, I'm Christy Patton-Lukes, and I'm teaching the summer version of Chemical Engineering 2100, Material and Energy Balances. So let's get started. I'm not really going to be talking about Chapter 1 particularly. Chapter 1 is kind of motivational. It's about some career choices that you might make based on a chemical engineering degree. You might read it now, but I really recommend coming back and reading it when you're at a low point in the semester and you feel like the work is too hard. Come back, read this, and become remotivated. So Chapter 2 is where the material really begins. Most of this should be review. If you are not comfortable with unit conversions, then you really need to practice this. But for the most part, I'm going to assume that you have some basic skills here. Now, one of the misconceptions people have is that there are tools that can do this, so why should they learn? Right? Your calculator might do it. I know Excel does it. There are numerous web tools that do unit conversions, and I use all of those. But you need to know the process. There are times when unique units show up, and as an engineer, you ought to be able to do these conversions on your own. So we often talk about units and dimensions, and we just kind of banter them around like everyone knows exactly what we mean. A dimension is something that you might measure. So a dimension might be length, it might be temperature. A unit is the scale that we are using to make that measurement. So maybe it's feet or centimeters, maybe it's degrees centigrade or degrees Fahrenheit. One thing that's really key is that whenever you give an answer with a measured value or the answer to a problem that you've manipulated those measurements, the answer has a numerical value plus units. When you don't include the units, the answer is technically just incorrect. Now, I'm very strict about this, and I know most other engineering faculty are also. But I frequently hear people say things like, oh, it's 110 outside today. It is so hot. Well, 110, I'm guessing you probably meant degrees Fahrenheit. But if you meant degrees C, it's not only very hot, it's like boiling hot, right? So giving the units is very important in pretty much every case, okay? You should not just assume that people know what units you're talking about. Now, we'll be doing a lot of unit conversions. If you have the actual physical textbook, the inside cover of the book has a listing of conversion factors. You also may wish to use a handout that I can provide for you, and you can just find these all over the place. But let's learn how to use them by doing some practice problems. So we'll start with an easy one. A typical class session is 50 minutes. How many milliseconds in that class session? Well, okay, minutes to seconds. We're all pretty good at that one, right? There's going to be 60 seconds in a minute. Milliseconds to seconds is going to be something milli is 10 to the minus 3, so 10 to the minus 3 seconds is a millisecond. If I put all those together, I want to do it in such a way that the units cancel top to bottom of a fraction. Now, for typesetting purposes, I've written them so that they go straight across. These are really easier to do if you write them out by hand, and then you can put the fractions so that they're one item over the other, 60 seconds per 1 minute. That's going to make things a little bit easier. But for typesetting, we've done it this way. Now, you can use combinations of things in all sorts of different ways, but you want to make sure that all the minutes in the top cancel minutes in the bottom, seconds in the top, seconds in the bottom. And I'm left with only milliseconds, and that's 3 times 10 to the 6th milliseconds. And man, when I updated this slide, I lost my milliseconds. Points off for me for no units. Now here's another one. It's not that this is a particularly hard problem, it's just that when you see something like this, the answer doesn't give you a direct instruction to change the units. So here we want to compare two cars, and one car is described as having 28 mile per gallon fuel economy, and another one has 19 kilometers per liter. Which of those is a better fuel economy? It's kind of hard to tell based on just that. So I want to convert one into the other units. Doesn't matter which way you did it. I chose to start with the 28 miles per gallon and turn that into kilometers per liter. So I've converted my miles to meters, meters to kilometers, and then my gallons, I converted those to liters. So when you do that, following the little breadcrumb trail here, I get that 28 miles per gallon is 11.9 kilometers per liter. Well, okay, that's a lot less than 19 kilometers per liter. So therefore, the second one is going to be more economical to drive. My next example, you may want to pause and read this and puzzle over this one for a while. This is an example that these are indeed standard units in certain niche parts of the economy, okay, but they're not standard units to most of us. But, okay, a cord of wood is a volume of wood that takes up 3.62 cubic meters. An acre foot is a volume that's used by people who do like management of water systems, and this is going to be how they describe the volume in, say, a pond. Okay? An acre, in that acre foot, is defined as a chain times a furlong, which would make great sense if we were living 200 years ago. A chain is 66 feet, and a furlong is 660 feet. So, a small lake has lost 5.8 acre-feet of water due to a drought. And what we want to do is we want to artificially bring that lake level back up by adding cords of wood. We're going to assume no airspace. And so how much wood would I need to dump in there to get it back to its original depth? Okay, now that's a bizarre thing to do. Totally fictitious, but we can do this problem. So if we interpret these things that were given in the statement here, we have one cord is 3.62 cubic meters, and an acre is 66 feet times 660 feet. Now the problem statement is asking about 5.8 acre feet. An acre foot is an acre multiplied by a foot. So 5.8 acres feet, so I want to get rid of the acre portion of that. So 1 acre is 6 times 660 square feet. And then, now that I've got feet times feet squared, so that's feet cubed. And I want to turn those into meters cubed so that I can get it then into cords. So a meter is 3.281 feet. I want to multiply that by that 3 times, or it's that expression to the third power. Don't forget about that little power out there. That's one of the common mistakes. And then a cord is 3.62 cubic meters. Turns out it would require about 2,000 cords of wood. So we have one more example here. This one is a bizarre one. I made up a word, okay? I wanted to purchase a rug. I went on a website, okay, a pretend website, and the rug is 128 geophos long, okay? Now, a geophos isn't a real unit, but if you go to that imaginary website, it says that a geophos is a unit of measure that's 13.6 centimeters long. And what I want to know is what's the length of the rug in feet so I can figure out if it fits in my house, and I know my measurements in feet. So, this is why you would need to know the process. 128 geophos, 1 geophos is 13.6 centimeters. 1 inch is 2.54 centimeters. 1 foot is 12 inches. Therefore, this rug is 57 feet long. Not going to fit in my house. I'll have to go back and find a different rug. One final comment for this lesson. Systems of units. We're going to be using a combination of SI units and American engineering, or sometimes called English units. When a problem is stated in a particular system of units, the final answer needs to be given in those same units. Now, your intermediate steps can be done with either one, but I do recommend minimizing the number of unit conversions for greater success at getting correct answers. So this concludes this first lesson, and in the next lesson we will continue with Chapter 2.